Hello, chemistry students. This is Professor Sean McMahon with our fourth lecture from chapter 4. In this chapter 4 is atoms and elements, and in this particular lecture, my focus is going to be on the electron arrangement. So with last lecture, I introduced the concept of light because to learn about the electron's locations, we had to discuss light and the similarities and how we use light to help us understand electrons and their different energy levels. We left off with atomic emission spectra and how when we put in energy into neon signs, for example, that have different elements and gaseous form, and we excite the electrons using the electrical energy, when they drop down and go to the ground state, or basically where they were located before, they have to release energy in some form. So there's an absorption of energy and then a release in energy. That releases in the form of light. And then we can take that light, shine it through a prism, and unlike the white light that we discussed last time, where we get a continuous spectrum, we actually get very distinct lines, okay? So that's with all atoms. And we could think of these lines as essentially a fingerprint for the different elements. So why is it that we're seeing individual lines? Well, Bohr formulated his model for the Bohr atom based on these atomic line emission spectra. Essentially, the movement of electrons were the reason for the atoms emitting light. The reason why they're lines is because there's only specific wavelengths of color that were allowed. So the transition of the electrons are actually between what are referred to as energy levels. So based on different positions where these electrons are relative to the nucleus, they are transitions between these energy levels. So an electron can change energy levels by either absorbing energy and going to a higher energy state, we'll say it's excited, and then they can actually drop down to lower energy levels, and as they drop down, they have to release that energy, and they release it as the form of light. So here's an example, a crude Bohr model, where it's showing, okay, here I have an electron. It's in the first energy level. So on the periodic table, we can think of that as period 1, row 1. If I put energy into it, I can excite it to a higher state. But like if I throw a ball up in the air, it's still attracted to, based on gravity, to the ground. What goes up is going to come back down. So as it drops down, we call that a relaxation. And it's an emission of light. So based on the distance that it drops, it's going to give us a different color, because the color, based on its wavelength, can kind of determine the amount of energy. So it's the electrons that determine the physical and chemical properties of atoms based on their location and their energy levels. So Niels Bohr speculated that electrons that orbit around the nucleus are in these fixed energy levels, and actually was able to quantize them for the hydrogen atom. So using the Bohr model to understand this, what we found is specific energy levels are where the electrons are located, and they can't be in between. It's either all or nothing. The lowest energy level is the one that's closest to the nucleus, and we use the letter N to show energy level. You can think of it as, it's referred to as a principal quantum number, but it's representing the period in the periodic table. So energy level 1 is the closest orbit to the nucleus. And then energy level 2 would be the next level, energy level 3 would be the third, and so on and so on. Bohr actually won the Nobel Prize for this in 1922, and for his quantized energy levels and his newly developed from the nuclear atom, the Bohr model. So electron energy levels. Electrons increase in energy, and the number as electrons get farther away from the nucleus. So what this means is, as the electrons get further away, you can think of it as more potential energy. So earlier in chapter 3, we talked about matter and energy, how there's kinetic energy, which is associated with movement, and then potential energy based on position. So as the energy levels increase, they're further and further away. They have more energy because there's a larger distance to the nucleus that carries the positively charged protons. The electrons in the energy level are negatively charged, and they have that attractive force. That's the potential energy. So the greater the distance, the more energy, the higher the energy level. And that's why when we go down on a periodic table, periods, as we get more protons, more atomic, the greater atomic number, we get more electrons, and they have to go further and further away because we can only fit so many next to the nucleus in each energy level. So the higher the electron energy levels, the more electrons it can hold. You can think of it as, if I'm really close to the nucleus, I can only fit a couple of electrons. Why? Because electrons repel one another. So they want to distance themselves, even though they want to get close to the nucleus that has the protons, they don't want to get too close to each other. But as I go further and further out, now that orbit is larger, so I can fit more electrons in. The more energy the electrons have. So basically, the further away I get from the nucleus, the more energy the electrons have, and the more electrons I can fit in that orbit or energy level. What's tricky for students is not so much the concept of periods being energy level 1, energy level 2, is within the energy levels, we actually have sublevels. And that's where it gets a little tricky. So within energy levels, you have sublevels that contain electrons, and within the sublevels, they have, different orientations. All the sublevels in the same energy level have the same amount of energy, but they are identified by different letters to show their position and orientation around the nucleus. So the number of sublevels in an energy level is equal to the energy level itself, which is, again, n, which is your principal quantum number. In this course, we don't deal with the 4 quantum numbers, but we introduce quantum number n, which shows the energy level, basically the period on the periodic table. So how does it work? You have the same number of sublevels as you do in the energy level. So energy level 1 only has one sublevel, and that's the S. So you have to fill the S first. And you have to fill the first energy level first. So you fill the first energy level, and it has an S sublevel. So you get your electrons. Then you have to go further out. Now this energy level, because it's further, those electrons are going to have more energy, but you could also fit more electrons. So now in the second energy level, you have 2 sublevels, S and P. In the third energy level, you have 3 sublevels, S, P, and D. And in the fourth energy level, you have 4, S, P, D, and F. And you can see as I go further and further away, there's more and more electrons. In fact, every sublevel can actually have more electrons, and we'll see that as well. So each electron sublevel consists of what are referred to as orbitals, okay? So I know with Bohr's model, we were talking about orbits, but in actuality, we have something that are called orbitals within these energy levels. And these are regions where there's the highest probability of finding an electron. So Bohr was able to quantize the energy levels, these orbits, for hydrogen, which worked really well when there was 1 electron. When there's multiple electrons, it doesn't work as well. So we had to use different mathematics. Basically, they're called wave functions, and that's where quantum mechanics were derived. So with multi-electron species, because of this, we had to develop a more suited atomic structure. And that's where, okay, we're going to refer within each energy level, there are also sublevels that contain orbitals, and orbitals are regions of space that 90% of the time, you're going to find the electron in that region of space. Each orbital can hold 2 electrons. Okay, so 2 electrons per orbital. And each orbital has a unique shape. So that's kind of what the letter is denoting, right? So S orbital, it's kind of spherical. Your P orbital, it's got this kind of, bilobal shape. Your D orbital is cloverleaf. And then your F orbital has kind of a more complicated shape because it's a further distance from the nucleus. So the electrons can be in greater probabilities in different locations. So the number of orbitals in a subshell varies. So in subshell 1, or subshell S, there's only one orbital. So in all, doesn't matter if you're in energy level 1, 2, 3, or 4, all of the S sublevels in those energy levels only have one orbital. That's why there's one box, okay? Now in energy level 1, I can only have one sublevel, that's S, and then there's only one orbital. There's 2 electrons per orbital. That's why if I go across the first row, there's only hydrogen and helium, because there's only 2 electrons in that 1s sublevel. If I go to the next energy level, now I'd go down the periodic table to period 2. The first 2 electrons, all right, I'm in energy level 2, I have 2 sublevels. The first 2 electrons will go in the 2s orbital, but then the remaining 6 will go into the 2p sublevel, but that actually has 3 orbitals. And then the third energy level that has 3 sublevels, the 3s sublevel has 1 orbital, the 3p has 3, but now with the D, you have 5. And then when I get to the 4th energy level, the sublevels, there's 4 of them. You still have your S, P, D, and now you have your F. A way you can remember this is it's consecutive odd. 1, 3, 5, 7. Each orbital, again, can only have 2 electrons. What you need to understand is even though the sublevels will have the same letters, because if they're in different energy levels, they're going to be further away and they're going to be bigger. So a 2s orbital is the same shape as a 1s, but it's larger because it's further away. Okay. If a 1s electron and a hydrogen transitions to a 2s, then the hydrogen is in what's referred to as an excited state. So we talked about how we can excite electrons with electricity, but then they can fall back down to where they belong, which is referred to as the ground state. So with electron orbitals, orbitals with the same subshell vary mainly in the orientation around an X, Y, and Z axis. So here's an example of the 3 2p orbitals that we talked about. So remember, energy level 1 has 1 sublevel. Energy level 2 has 2 sublevels. Energy level 3 has 3 sublevels. Energy level 4 has 4 sublevels. In energy level 1, the 1 sublevel is S. In energy level 2, the 2 sublevels are S and P. And if you recall, I'll go back, the P has 3 orbitals, the S has 1. Why? Well, the S is this spherical shape. So only 2 electrons can fit in those spheres. When I go further out now, I have because now we're dealing with 3D, right? So when you graph in algebra, like with your Y and X axis, that's flat, right? That's a 2D model. That's Cartesian coordinates. But in 3D, you learn this in calculus, polar coordinates, you have to have 3 axes. So you have your Z, your Y, and your X. So if this is my 2S, my 2P's are going to go along the axis. So that would be 2py, 2px, and 2pz. The y is going out of and into the plane. So they draw it at a diagonal to try to show that it's going like that, okay? And the reason why I can fit this is they're further away than the 2s or the 1s. So that's what their orientation is. So there's the y, the x, the y, the z axis, and I can have the 3 orbitals based on those axes. I can have 2 electrons per orbital. So in this px orbital, I can have 2 electrons. You know, maybe one's right here and one's right here. This 2py, I can have another. And then this 2pz, I could have another 2. So all of these add up to 6 electrons in the p subshell. So electrons actually do have what's called an intrinsic spin property. So they can spin up or down. So you can think of it as like a magnetic pole. You can spin clockwise or you can spin counterclockwise. And they actually spin in opposite directions. So the way we denote that is using arrows either up or down. Pauli's exclusion principle is saying you can only have 2 electrons in one orbital, and they have to have opposite spins. So we use what are called electron configurations or orbital diagrams to basically keep track of the electrons and show where they're located. It's basically like bookkeeping or writing a checkbook. You have to know, what goes in and what goes out. Well, it's the same thing with electron configurations and orbital diagrams. It lets us know how many electrons there are, what energy level they're in, what sublevel, and which orbitals, and whether they're spinning up or down. So energy levels are filled with electrons, and it's in order of increasing energy. So you always start with the first energy level 1, and then you start within each energy level with sublevel S. Once you go to the second energy level, then it's SP. Once you go to the third, because you have 3 sublevels, SPD. And once you go to the fourth, SPD and F. So an electron configuration just shows where the electrons are. So hydrogen has 1 electron, and it's in the 1s orbital. So we write 1s1. Helium has 2 electrons, and it's in the first period. We see that. So it's in energy level 1, and there's only 1 sublevel S. So it has to be a 1s. There's only 1 orbital for the s, so it's a 1s. And then there's 2 electrons because the atomic number is 2. So it's a 1s2. So with this particular periodic table, and honestly, all the periodic tables, but what I'm showing right here, I'm trying to move something, is that here is my hydrogen, atomic number 1, which means 1 electron. Here's my helium. Atomic number 2, which means 2 protons, but if I have 2 protons, I have 2 electrons. You could really put that box right here. The reason why I'm showing you is when you go from left to right on your rows, your periods on the periodic table, you hit 2 columns. Remember, this is group 1A and group 2A. Those 2 columns actually represent the s orbital. When you cross over to this block, there's 6 columns. Those 6 columns represent the 3 p orbitals that we had just talked about, px, py, pz. The D block and F block are a little trickier, but there's 10 columns, and then there's 14 columns for the F. So we'll see that this is F, this in here is D, this is S, and this is P. And the nice thing is you can figure out how many electrons are in each sublevel by counting the number of columns. Okay, so if I look, right, I said hydrogen was a 1s1. Why is that? This is period 1, This is my S block, and it's in the first position. Helium is a 1s2. Why? Energy level 1, second position, 2 electrons, because it has 2 protons, and it's in the S block. After I fill this first energy level, I have to drop down to the second. So remember, S can hold only 2 electrons, P can hold 6, D can hold 10, and F can hold 14. Right? So that's my S area, that's my P area, my D, and my F. So I'm splitting the periodic table to help me understand where the electrons are, what sublevels. So I can use the periods, like this is period 1, 2, 3, 4, 5, 6. So I can use the periods, which are energy levels, to tell me how far they are. And then I can use the areas in the periodic table to tell me where the electrons, what sublevel they're located in. So if I'm in the first column, my last electron is an S1. So it's in sublevel S, it's 1 electron in there. If I'm in the second column, the last electron is in an S sublevel, but it's the second electron. And remember, each orbital, remember the S is spherical, has 2 electrons. So there's only 1 S orbital, right? There's only 1, and I can only have 2 electrons. Spin up, spin down. When I go to the second energy level, I can have 2 sublevels. I can have the S and the P. And now with the P, there's 6 positions. Why is that? Well, I can have a PX, PY, and a PZ. And if you remember, those were, well, that would be PZ, but your PY and your PX. So 2 electrons in each. So, and we'll learn that we're going to be filling this up. You first, according to Hund's rule, is you put an electron in an empty orbital in the same sublevel first, because you want to minimize repulsion. So if the first electron in an orbital, in a sublevel, is going to go into an empty orbital, the next electron, if it has a choice to go into PX, where there's another electron that repels, or an empty PY, it's going to go into the PY. So typically they go into empty orbitals with parallel spins, and then once all the orbitals are halfway filled, then you would start filling them up. Okay. But again, your periodic table pretty much does the work for you. Okay, so we're going to use the periods. We're going to use the areas. So remember, this was group 1 and 2 is the S area. 3A through 8A is your P area. And then the transition metals are your D. And then down here, the intertransition elements are your F. So D orbital filling is a little tricky. And the reason is, once we get to the D sublevel, the numbers are actually 1 less than the period number. So they're shifted down, but it looks like they're in the 4th period, but they're actually in the 3rd energy level. And the reason why is the 4S actually fills up before the 3D. They're very close in energy. The 4S is slightly lower, so you fill that up first. Okay. The F orbital fills up 2 less. So you would start with 6S and then drop down to 4F and go across. Then you would come back up, go D, 5D, and then go across 6P. Now, what you can use to help you is the atomic number on the periodic tables. Okay. So that's pretty much the best way to do it, okay, is using the periodic table. So what you'll notice is in the 4th period, I first fill up the 4S with the 2 electrons. So fourth energy level, the first sublevel is S, but then I go to the D sublevel here, but it's one behind. So it's a little tricky. Just remember, it's always one behind. So here, if you look, once I go to this transition metals, the D block elements in orange, they're one behind. So this is 5 and this is 4. This is 6 and this is 5, 7, and 6. The D block is always one behind. The F block is 2 behind. So if I start period 6, I go 6s1, 6s2, 6s2, d1, but then it drops down here. And it's a little tricky, but if you use the atomic number, you see I go from 57 not to 72. I have to drop down here to the F block. And that actually starts it at 4F because the F block is 2 behind the period of 6. For this course, I tend not to do too many Fs, but I do like to bring that up. When you're looking at this, again, you see this is a 1s1. Helium has 2 electrons, so it's a 1s2. Once I get to the second energy level, right? Lithium has 3 electrons. Where do the first 2 go? Well, the first 2 have to go into the first period. So if I go across, there's 2 electrons and they go into the 1s2. And then the third electron has to go where? In the next energy level. That's why the elemental symbol lithium is in the second energy level. So I have to go to the second energy level. I'm in this S area. So I'm in an S sublevel. And then I'm in position 1, group 1. So I have 1 electron in the second energy level in the S sublevel, and I have 1 electron there. Beryllium has 4 electrons. So where do they go? Well, again, the first 2 go in the 1s2. And then the third would be a 2s1, but the fourth would be a 2s2. Now, how do I know it's 2s2? It's in the second energy level. I first fill up the first, which only can have 2, and then I go 2s1, 2s2, because I'm in the second position. When I get to boron, I have a total of 5 electrons. Where do the first 2 go? Period 1, 1s2. Then the next 2 go 2s1, 2s2. But I have 1 more because 2 plus 2 is 4. I have a 5th. Where does that go? Well, now I'm still in the second energy level, but now I'm in a new sublevel. What's my new sublevel? The P, because I'm over in the P block. And in the P block, I'm in that first box. That means I only have 1 electron in the 2p, so it's 2p1. If I go to carbon, it has 6 electrons. The 6th electron, where is it? It's still in the 2p sublevel, but I have 2 electrons in it. So now it's 2p2. And when I add this all up, this adds up to 2, 4, 6. I have 6 protons, so I have 6 electrons. I'm going to do more because I know this is a little tricky for people always. But I do want to mention one thing. When you refer to periods, what you want to always look at is the one with the highest energy level. So if I look at radon right here, it's in the 6th period. So I would consider this a 6th period element. Okay. So how can I use the periodic table to actually write an electron configuration? Let's just pick, let's pick arsenic. All right. So arsenic is located right here on your periodic table. So that's group 5A. And period 4. Okay. So what you need to know is essentially you're in the 4th energy level because it's period 4. You're in the P block. This is the P block, and you're in position 1, 2, 3 of the P block. That's why it's a 4p3. So you have to write out the configuration up to what's called 4p3. So how do I do that? Well, 1 electron would be 1s1, 2 would be 1s2, and then the first energy level is filled with 2 electrons. So I'm just going to write 1s2 because I can't put any more. When I go to the second energy level, I have 2 sublevels. I have the S sublevel, remember this is S, and I have the P. So my next set of electrons are going to go into the 2s1 and a 2s2, but there's only one orbital in the S sublevel, so after 2 electrons, I'm full. So where do the next number of electrons go? Well, I'll be over here. I'm in my second period because n equals 2, but now I'm in the P block. So this would be 2p1. This would be 2p2. This is 2p3 because it's in the 3rd position. 2p4, whoops, 2p5, and then 2p6. Now, why is it 2p6 for the noble gases? Remember, the P sublevel had your PZ, your PX, and your PY sublevels in each, or I'm sorry, orbitals in that P sublevel. So you have 3 orbitals. Each orbital, right? We have 3 orbitals. We'll just say PZ, PX, PY. Each orbital can have 2 electrons, making the P sublevel, that's this, have 6 electrons. But we don't even need to memorize anything. I can just count. There's 1, 2, 3, 4, 5, 6 positions in the P block. So that means 6 electrons go in there. So that's why the noble gases are happy, because they have a 2p6. So now I can write, if I'm doing arsenic, 2p6, because all of my second energy levels filled, but then I would go down to the 3rd. So this position's 3s1, 3s2. As I go across, 3p1, 3p2, 3p3, 3p4, 3p5, and 3p6. That's argon, so I'd write a 3p6. And then this is 4s1, 4s2, and this is where it's tricky. Right here, remember, the D is 1 behind. So I'm no longer 4 in the, even though this is energy level 4, the D sublevel is 1 behind. So this would be 3D1, D2, D3. This is actually not, there's an exception, but for now, I'm going to make it easy. This is 3D4, 3D5, 3D6, 3D7, 3D8, 3D9, 3D10. This is actually not, there's an exception to this, but I'm just trying to make it easy. But to go all the way across, now I'm going to have a 3D10. And then I still have a few more electrons. How many? 1, 2, 3, which lands me at a 4p3. So that would be considered an entire electron configuration for arsenic. So I'm showing all the electrons. How many electrons are there? 3, plus 10, 13, 19, 21, 27, 29, 31. So there's 31 electrons, and those are the positions. I must have counted that wrong. Wait. 2, 4, 10, 12, 18. Yeah. 20, 30, 33. I'm sorry. It's 33 electrons. So it's in the 33rd position. So can we write electron configurations for other elements? Okay, let's try it. If I look at the periodic table, right, for magnesium, how do I get 1s2, 2s2, 2p6, 3s2? So magnesium is here. What is that? The last electron is in the 3rd energy level. This is my S sublevel, and it's in position 1, 2. So the last electron is a 3s2. But how did I fill it up? Right? I had a 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6, 3s1, 3s2. So I can look at where it's located and figure it out. If I go to sulfur, where is it? Sulfur is right here. So it's also in the 3rd energy level, but now it's no longer in the S block, it's in the P block. And what position? 1, 2, 3, 4. Now, a lot of people get confused because they see the 6A. That 6 means in the 3rd energy level, there's 6 electrons, which in the 3rd energy level, how do I know 3rd energy level? That's what this number shows me. There's 6 electrons. That's why it's group 6A. But the first 2 go in the S sublevel, and then the 1, 2, 3, 4, the additional 4 go in the P. That's why it's a 3p4. Gallium's a little trickier. Why? It's all the way over here. So what is it? 4th energy level. It's in the P block as well in that first position. So it's a 4p1. But notice, to get there, I had to go from 4s2 across to 3d10 and then 4p1. Okay. But there's basically 2 types of electrons, right? There's what's in the core, and what I mean by core, it's embedded inside. And then really what determines physical and chemical properties are the electrons in the outer energy level. And those are called the valence electrons. And those are the ones that are most important for reactivity, because that outer shell wants to be filled with electrons to be stable. So that's where we exchange electrons. That's where we share electrons or lose or gain. That outermost principal energy level is called valence electrons. So with selenium, it's in the 4th energy level, in the P block, in the 4th position. Okay. When I look, the highest energy level associated is with the 4th. Okay, the 4s. So I like to say that all of these are your core. I still include, I know right here the arrow, I still include that 3D as part of the valence electrons because it's still in that same row as period 4. Okay. So if I look, where's selenium? It's right here, which is what? Let me remove that. It's in the 4th energy level, in the P block, in the 1, 2, 3, 4th position, so 4p4. If I was to go backwards, 4p4, 3d10, 4s2, 3p6, 3s2, 2p6, 2s2, 1s2. So you can also work backwards, but you first fill first energy level, which has one sublevel, S, which has one orbital, which has 2 electrons. How do I know? Because there's 1, 2 positions. Then I go to the second energy level, which has 2 sublevels, S and P, right? So as I go across the second period, I'm filling the 2s2, so 1, 2, 2s2, and then 1, 2, 3, 4, 5, 6, the 2p6. Why 2p6? Second energy level, P block, I go all the way across. Then I go to the third energy level, 3s2, 3p6, that's done. That's considered core because all of those levels are filled. And the noble gases, right? So helium is when you fill the first energy level. Neon's when you fill the second. Argon's when you fill the third. But now I have to go to the outer shell, the valence electrons, and I go 4s2 right there. And then the D is always one behind, my 3d10, and then finally my 4p4. And I consider those my valence electrons. So why am I bringing up core and valence? Because with electron configurations, there's the expanded electron configuration, and then there's the condensed. I like the condensed, although sometimes I will ask you to write the full electron configuration, but the condensed is I can use the previous noble gas, put it in brackets to show that those core electrons are filled. So here's an example. You can grab a periodic table, take a look, but iron is in the 4th period, but it's in the D block, which is always one behind, and in the D block, it's in the 6th position, okay? Argon is a noble gas for the 3rd energy level, and it's up to 3p6 filled, and it's happy. So a lot of times what people do is they take those core electrons that are not part of the outer shell and they substitute the noble gas that's in that p6 position. With the case of helium, it would be p2, or 1s2. But that's what we do. So for a condensed version, you can take the argon, put it in brackets, and that covers all of this, so you don't have to write this all out. And then you're left with 4s2, 3d6. So that's where you would drop down to the final period, the final row, and just fill out the remaining electrons to keep track of. So the core electrons are the 18 electrons that we see, like argon. And then there's 8 valence electrons, the 4s2 and the 3d6. Again, for transition metals, that D block, I actually included in the valence shell because it's filling up after the S anyways. So let's practice using the periodic table, right? Just get comfortable with maybe some easier electron configurations, and let's do it for phosphorus, right? So if I look at phosphorus on the periodic table, right? It's in the 3rd energy level. So the elemental symbols in 3rd energy level. It's in my P block, and it's in the position 1, 2, 3. So that means I have 3p3 filled and everything below it, because the 3p3 is the furthest one away from the nucleus. So everything below it is filled. Right? So I could write out for phosphorus, if I write out the full, right? Because here's 1s1, 1s2, 2s1, 2s2, 2p1, 2p2, 2p3, 2p4, 2p5, 2p6. So the second energy level's filled, I go 2s2, 2p6. Then I go to the 3rd energy level, 3s1, 3s2, 3p1, 3p2, 3p3, and I could write 3s2, 3p3. That's the full. But if I want to do the shorthand version, I can use the inner electron configuration. So I look at the noble gas just above it, which is neon, which is filled up to right there because it's a 2p6 position, and I can just write neon and then write the third energy level where it's found, just the valence electrons 3s2 and 3p3. So that is the shorthand version of phosphorus. So can we do it for arsenic? Well, I wrote it out earlier, the long version, but now if I look at the core electrons, right, it's the same as argon, right? Because we have the 1s2, the 2s2, the 2p6, the 3s2, the 3p6 like argon, excuse me, and now all I'm going to write is the outer shell that needs to be taken into account. So 4s1, 4s2, again, going all the way across, 3d10, and then 4p3, because it's in the fourth energy level in the p block in the third position. Again, the tricky part is that D is always one behind. So pause this, look at a periodic table, and try to write out the condensed electron configurations for these. And then, well, now we can go over it together. So you need a periodic table. So where do we find silicon? So where's the noble gas in, the core electrons that's closest to it? Neon. So I can write in brackets neon, which shows that I have a 1s2, 2s2, 2p6, and then just write the valence electrons, the 3s2, 1, 2 in the s block, and the 1, 2, 3p2. So neon, 3s2, 3p2. Now, what about calcium? So let me erase, these. Calcium's right here. Okay. So for a shortcut, if I look, right, it's in the fourth energy level, but it has a third energy core filled up to argon. So I can write bracket argon and then 4s1, 4s2. That's condensed. What about nickel? So again, fourth period, but remember, this is the D block. The D block messes people up. It's one behind. So the shortcut is going to be argon because that's the last noble gas to be filled. It's going to be a 4s1, 2, just like calcium. But now I'm going to add 3d1. So d1, d2, d3, 4, 5, 6, 7, 8. So it's a 4s2, 3d8. Iodine. So this is why we want to use shorthand, because for a lot of the elements that have way more electrons, right? So when you go down and to the right, we're getting more and more electrons because left to right, top to bottom is increasing atomic number, the increasing number of protons. So as we get to the lower right-hand side, we have a lot of electrons. So we want to use a shorthand. Where's iodine? It's right there. What's the last noble gas to be filled? It's almost like xenon. That's why it's so reactive, but the last to be filled is krypton. So I could put krypton in brackets, and then I would write, this is the fifth energy level, 5s2, 4d10, and then 4p, or 5p, sorry, 5p, 1, 2, 3, 4, 5. All right. Where does it get tricky? Polonium. This is really hard. I picked the hard one. Why? The shortcut is easy. All right, let me get rid of the iodine stuff. Here's polonium. It's in period 6. The last noble gas to fill is xenon. But we would go 6s2. But remember, if I look at the numbers, 57, 72, what happened? I dropped down, and they even tell you 6 right here. I drop down here, and now I start the F block. But remember, the D block is 1 behind the period. The F block is 2 behind the period. So to get to iodine or polonium, which is over here, I would go 6s2. I have to drop down, and I can use the atomic number, and I see that I go 4f14. How come? 1, 2, 3, 4. And I can write it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 4f14, because we're 2 behind. Then I go all the way back up here. And now this is 6. So this is this region right here is 5d10. And then I go 6p1, 2, 3, 4. So I go all the way up to 6p4, but it's tricky because I have to have the 6s2, drop down to the 4f14, come back, go to the 5d10, and then the 6p4. So it's a little bit tricky for sure, no doubt. I find electron configurations, students have to practice it quite a bit, okay? But I like giving easier ones and some harder ones. I typically in my quizzes and tests, I don't do too many with F, but I wanted to show you one with the Fs so that you know how to work it. Now earlier we had talked about inside, right, buried are the core electrons. That's why we were using this shorthand version where all of this inside, this is filled core electrons. So we don't, when we're looking at polonium, you got the 1s2, the 2s2, and then the 2p6. Then you go to the third energy with the s, p, and d. Then you get to the fourth, the fifth. So all the way out here, you deal with the 6th energy level. That's where the electrons are going to be exchanged. So we're really only concerned with these valence electrons because those are the electrons that are involved in reactions. What do I mean by that? Earlier, I had talked about bonds are basically sharing electrons, okay? When atoms first come in contact, the electrons that are going to come in contact first are the ones that are furthest away from the nucleus because they're on the outer surface of the atom. So those are the first ones that come in contact with other atoms. So it's the valence electrons in the outermost shell where we have the bond formation and the exchanging of electrons. So we're only interested in those valence electrons. With electron configuration, you can write all the electrons in the full, or we were doing the condensed, the shorthand version, where we shortcut the core with the noble gas. But when we do orbital diagrams, to show the number of not just sublevels, the number of orbitals in each sublevel and the spin of the electrons, we only want you to write the valence electrons, and we're using boxes and arrows. The box shows the number of orbitals, the arrow shows the electrons and their spin. And again, each box is an orbital. Each orbital can only have 2 electrons. They have to be opposite spin. So hydrogen's first, it has only 1 electron, so it's a 1s1. So I draw 1 box because there's only one orbital in the 1s sublevel, and I put one electron in. So what happens when there's two electrons? Well, because helium's in the first energy level, which only has one sublevel, the S, the box is labeled 1s because it's in the first period. There's only one sublevel S, but there's two electrons, so now the second electron spin down. So what about iron that has the condensed configuration, and we did this one earlier, of argon 4s2 3d6. The argon's representing the core electron. So when we do orbital diagrams, we don't need to draw all those boxes. We're only going to focus on the valence electrons, which is the 4s sublevel and the 3d sublevel. So how are we going to do that? 4s, one box. Why? On your periodic table, the S block has only two positions. Two electrons can go on that S sublevel. Each orbital has two electrons. So if there's only two electrons in the sublevel, there's one orbital. The D block, if you count the Ds, there's 10 columns, right, on the periodic table. That means 10 electrons can go on that D sublevel. Each orbital, right, can have two electrons. So 10 divided by 2 would give me 5 orbitals. So how would I fill that out? Well, according to the building up principle or the Aufbau principle, right, you're going to start with the subshells that are increasing in energy, right? So, but basically you're going to start with the 4s. You just use the periodic table, and you have the two electrons in the 4s. But when you go to the 3d, you have to follow Hund's rule. And again, I said this earlier, with Hund's rule, you're basically going to go into an empty orbital first. So I need to add 6 electrons. How am I going to add it? I'm first going to fill each orbital with 1 electron. There's 5 orbitals. And then the 6th electron is going to go in a half-filled orbital in an anti-parallel spin. So there's still 4 more of these 3D orbitals that are only half filled. So what does that mean? If they're half filled, iron has 4 unpaired electrons. So if we go back to what we did earlier, right, in exercise 7, if you remember silicon, right, if we look, it's right here. So what is that? If we did the shorthand version, it was what? Neon. So we're not worried about the core, but then we go 3s2, 1, 2, and then 3p, 1, 2, 3, 4, 3p4. Okay. But when we're doing orbital diagrams, right, 2 electrons per orbital. In the S block, 2 electrons go in. 2 electrons divided by 2 electrons means there's only one 3s orbital. I don't draw boxes because then people get confused with the periodic table. I just draw a line. That represents the one 3s orbital, which, remember, it's spherical, just like the 1s and the 2s is just further away. But then I have to go to the P. And if I look at the P block, if you remember, there's 6 positions, 6 electrons. So there's 6 electrons, 2 electrons per orbital. How many orbitals? Well, 6 divided by 2 is 3 orbitals. Why is that? Remember, we did this earlier. They're the bilobal. You have your P, X, PY, PZs. So I would draw 1, 2, 3 boxes or lines for my 3p sublevel. And now I'm going to fill the electrons. So I have in sublevel 3s 2 electrons. So first spin up. There's only 1 orbital. Spin down, it's full. Then I go to the next sublevel, the 3p, which could have 6 electrons but 3 orbitals. And I follow Hund's rule, where I first fill an empty, an electron's going to minimize repulsion by going into an empty orbital first. So this would be 3p1, 3p2, 3p3, and now 3p4. So there's 2 3p orbitals that are half filled. So how many unpaired electrons? Can't see it because I wrote all that. 2. I shouldn't have erased that. 2, because of the 3p4 left me with 2. Yeah. Left me with 2 unpaired electrons. So if I was to do it to calcium, right? If I look at calcium, it's right here. Noble gas, I would go to argon. So it would be argon. What position is it in? 1, 2, 4s2. If I was to draw the orbital diagram, I'm only looking at the valence shell. There's only 1 4s orbital, so 1, 2. There's no unpaired electrons for that. So that should be 0. What about nickel? Right? Do we remember what nickel was? So here's nickel. Shortcut, we're going to do argon. So we have, argon. Then we come down, we're going to have a 4s2, 3d, but how many? 1, 2, 3, 4, 5, 6, 7, 8. So it's a 3d8. Now this is where it's tricky. We have to figure out how many orbitals. Okay. So we're only doing it for the valence electrons. Which ones are the valence electrons? Anything outside of this argon shortcut configuration, those are all core. So the 4s, if you remember, there's 1 orbital in the s sublevel. Why? The s block has 2 positions. How many orbitals in the d sublevel? This is where students get a little tricked up. Don't. If I look at my d block, how many positions? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So because there's 10 positions, that means 10 electrons can go in the d sublevel, right? But I can only have 2 electrons per orbital. So how many orbitals? 10 divided by 2, 5. So then for the d, I would go 1, 2, 3, 4, 5. Right? And it's a d8. So now let's clean this up a little bit. It's a d8. It's in that d8 position. So the 4s2 is filled. d8. I follow Hund's rule. 1, 2, 3, 4, 5, 6, 7, 8. How many unpaired electrons? 2. Because 2 of the 5 orbitals are halfway filled. Right? If I had a 3d9, like in copper, it's going to go in there. There's an exception. But if I get to zinc, which is 3d10, then both of these are going to be filled. So how many unpaired right now for nickel? 2. Now, when I get to iodine, right? And you'll start getting better at the shortcuts, right? So, whoops. Krypton. If I'm doing the configuration, it's krypton. And then to get to iodine, it's 5s2, 4d10, 1, 2, 3, 4, 5, 5p5. If I look, now I'm getting a little bit more fluid with this. If I look, the 5s2, I know is the one orbital's filled. How do I know that? Because there's only two positions and it's filled. The 4d10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 4d10, all of the electrons fill that sublevel. That's why I had to move to the 5p5. So really, to answer how many unpaired, I just need to go 5p sublevel. 1, 2, 3, 5 p's. Why? Px, py, pz. So px, py, pz. There's 3 orbitals in the p block. How do I know that? Here's the p block. How many positions? 1, 2, 3, 4, 5, 6. 6 divided by 2 equals my 3p orbitals. They're the same shape as 2p, 3p, 4p, but if they're in the 5th energy level, they're just further away from the nucleus, but they have the same shape. And that sublevel only has 3 5p orbitals. I'm a 5p5, so I go 1, 2, 3. They're all halfway filled. 4, 5. There's only one unpaired electron. Okay. So now we can do that same little cheat that I did this time because it's taking a little bit longer. This is a longer lecture than I anticipated, but this is hard stuff. I hope I didn't confuse. I'm sure I did. But you can pause it, go back, practice. You also have the book, but let's go to the, polonium. If I go to polonium, I know I'm xenon. I'm going to do it down here, xenon. Then this is the, oh, Sean, why'd you do this? To challenge you. 6s2. Remember, it dropped down to 4f14. Right? And how do I know? Because I went 58 to 59, all the way to 71. Then it comes all the way back to 72 for atomic number. So now, right, the F block is 2 behind the energy level. When I come back up, the D block is 1. So this is 5d10. So all that bad boy is filled. And then I get to 6p, 1, 2, 3, 4. So 6p4. So S2 is filled. This is all filled. All the F14 is filled. There's 14. All the D10 is filled. What did I not fill? Because to be filled, I'd be radon, but I'm not quite there. How many do I have in that P block? It's in the 4th position. 1, 2, 3, 4. So it's a 6p4. So I would go 1, 2, 3 orbitals, right? 6p has 3 orbitals. Why? Again, the block has 6 positions divided by 2 equals 3 orbitals. How many electrons in polonium are in the 6p sublevel that has 3p orbitals? 1, 2, 3, 4. So how many unpaired electrons for polonium? 2. For the 2 half-filled 6p orbitals. And that makes sense because to fill these, I need 2 more, right? How far away am I from a noble gas? 1, 2. I want to be like radon, radon. But I need 2 more electrons to be, if I'm polonium, I want 2 more electrons to be like radium. Why? Because my 6p sublevel has 2 unpaired orbitals that need 1 more anti-parallel spill electron. So I need 2 more. So I have 2 unpaired electrons. That's going to be important later when we're doing ionic compounds to determine the charges. So now we talked about valence electrons. Now we can go back to how we stacked the electrons in these groups, these families, in these vertical columns, and why they had similar physical and chemical properties, why Mendeleev was able to do that. And it has to do with the number of valence electrons, right? So group 1A, right? If we look at group 1A, if you go down the group, it starts with hydrogen, but below it is lithium. Well, what do we know about lithium? Its electron configuration is 2s1. What does that mean? In the second energy level, there's one valence electron. It's in an S sublevel, and there's only one. If I go down another period to the third row, well, sodium, third energy level, it's in the S block, and there's only one 3s electron. So it's a 3s1. But again, the core electrons are not reacting. It's the valence. And if you look, lithium and sodium, they both have one valence electron. That's why they're in group 1A, because they have one valence electron. So does potassium. That's why potassium's in group 1A. The only difference is their energy levels, right? This is, so I should do, here's hydrogen. Hydrogen's a 1s1. It has one valence electron. Lithium, the energy level's 2. So 2s, why is there 3 electrons, 3 protons? 2 go in the first energy level and then 1 in the second. Sodium, it's in the third energy level. Why? It has 11 protons, 11 electrons. The first 2 go in the first energy level. The next 8 go into the 2 sublevels in the second energy level, S and P sublevel. So that's 2s2, 2p6. If you've heard of the octet rule, there's your octet. When the S and P sublevels are filled, 2 electrons are in the S sublevel, 6 are in the P sublevel because there's 3 orbitals. 6 plus 2 is 8, octet rule. Noble gases have an octet. That's why they're in group 8A. But sodium is in group 1A because its 11th electron goes into the third energy level in the S block in the first position. Potassium, 4th energy level, S block first position. Rubidium, 5th energy level, S block first position. All of these are in group 1A. They're all alkali metals because they have the same number of valence electrons. Look at the halogens. Why are they all in group 7A? Because they have 7 valence electrons. Where are the 7 valence electrons? Well, if I go left to right, the first 2 go in the S block, and then the next 5 go into the P block or the P sublevel, and they're in the 5th position of that P sublevel. That's why they're P5. And 2 plus 5 makes group 7A because they have 7 valence electrons. Same with chlorine. It's just down the periodic table, it has an additional energy level, 3rd energy level, instead of 2nd. So just further away. Yeah. So iodine, with the orbital diagrams, I had you include the D, but again, for valence electrons, so orbital diagrams include the D block, but for valence electrons, really, we're looking at just the 5th energy level, and there's 7. That's why iodine's in group 7A, the halogens. Because there's, oh God, that's really sloppy, I'm sorry. There's a 5s2 and a 5p5. 2 plus 5 is 7. Why is that important? Well, eventually we're going to do what's called Lewis dot structures, where we actually sketch out molecules and how they're connected based on their valence electrons, because that's where the electrons are being shared. So we have to be able to draw Lewis dot structures because they help us determine molecular shape. Molecular shape helps us understand properties like boiling point, solubility, whether I found it as a solid, liquid, or gas, based on the shape. So now, before we can get there, we have to understand, well, the valence electrons are what we're looking at when we talk about atoms, because again, I have the dense nucleus with the protons and the neutrons. Electrons are trying to get close to the protons, but they repel each other. So in that first little orbital, I can only fit 2. But as I go further out, those electrons have more energy because they're a greater distance from the nucleus, and I could have more. So the second energy level, I could have 8 octet. Third energy level, now I have 3 sublevels, S, P, and D. So the D can have 10 more electrons, so I add 10 to the 18, and so on. But with the electron dot symbol, I don't care about the core. I only care about the outer shell. And how do I shortcut showing the number of electrons? I draw the symbol with dots. So it's called the dot structure. So if I look at oxygen, it's a 1s2, 2s2, 2p4. Look at a periodic table. Even though it's group 6a, that's the number of valence electrons in the second energy level. Okay? So how am I going to draw the 6 valence electrons? 6 dots. So I draw oxygen, and I start by not pairing them. So basically I go 1, 2, 3, 4 sides, and now I have to pair them. So I go 2, sorry, let me redo that. I'm sorry, my bad. I start with 4 sides, 1, 2, 3, 4, and then I need 6, 5, 6. So oxygen has 6 valence electrons, 6 dots. Now hydrogen, if you recall, is in group 1a, so it has 1 valence electrons. Just like oxygen's group 6a, it has 6 valence electrons. That's what the A tells me. How many valence electrons? Doesn't break it down to S and P sublevels. It's just total valence electrons. Well, oxygen is 2 away from neon. It wants to be neon. But neon has, it's in group 8a, 8 valence electrons. Oxygen only has 6. Well, hydrogen has 1 valence electron, so we draw 1 dot. Okay, but hydrogen wants to be like helium, which has 2 electrons. It has 2 valence electrons. So as the hydrogens approach the oxygen, they're willing to share these electrons, because really these electrons are orbitals, right? And when they approach these orbitals, which are regions in space, begin to overlap. This is very crude, but I think it gets the point. And we draw that overlapping region of space now, because as they approach, they can share their electrons, and we draw it as bonds, which we draw lines. And there's H2O, right? So why does oxygen bind with 2 hydrogens, right? Because it needs 2 more electrons to be like neon. So what do? Hydrogen approaches, shares its electron with the 1 odd electron in oxygen, and forms a bond. And there's H2O. And now oxygen's happy. It has an octet. It has 2, 4. There's 2 electrons per bond. So 2 electrons per bond that are shared. So 2, 4, 6, 8. Has an octet. It's like neon. It's happy. And hydrogen's happy because it wants to be like helium and have 2 electrons. And it has 2 electrons there. So we're not going to worry too much exactly, how we place the dots. It just start with single on 4 sides and then pair them up. And if you look across the periodic table, we can use the group number to help us figure out the number of valence electrons that are being around each atom. So again, group 1a, let's look at lithium. It's group 1, it's a 2s1. So its valence shell is a second energy level. and it's an S1, so there's one dot because it has one valence electron. Group 2A, second energy level, it's a 2s2, so 2 dots. Group 3A is a little trickier. Why? 3 valence electron. The first 2 go into 2s, and then the third goes into 2p, but there's 3 valence electrons, so we drew 3 dots. Carbon, group 4A, 4 dots. That's why carbon likes to have 4 bonds. That's why it's a central atom, because it can form 4 bonds. Nitrogen, group 5A. How do I know? It has 5 valence electrons, 2s2, 2p3. I draw 5 dots, 1, 2, 3, 4, 5. It has 3 unpaired electrons, 1, 2, 3. Likes to have 3 bonds. That's why we see ammonia. NH3. Right, carbon, you see CH4, methane, because it likes to have 4 bonds. We just did oxygen, right? And then last, but by no means least, group 7A, the halogens, the reason why they're so reactive, they almost have 8. They have 7. That's why they're group 7A. 2s2, 2p5, 2 plus 5 is 7, so 7 dots. They need just one more to fill their S and P sublevels to be happy and be like neon. So they're extremely reactive, and that's why they're willing to share an electron with hydrogen that has an unpaired, because remember, hydrogen's orbital. It only has 1 valence electron, but it wants to fill this 1s sublevel. So as it approaches the fluorine, they share that electron, they form a bond. So for sample exercise 9, sulfur. Can you draw the loose dot structure? Well, you look on the periodic table, sulfur is in group 6A. How do I know? Right here, 6A. Now someone might say, well, wait, you just said that's a 3p4. It is a 3p4. You're good with the electron configuration. It's a 3p4, but remember, for the valence shell, we're counting all sublevels, right? So there's also a 3s2 and an s2 and a p4. 2 plus 4 is group 6A. So this has 6 dots. Oh, sorry. You got to have them unpaired. I was cutting 2, 3, 4, 5, 6. So you can imagine sulfur likes to have 2 bonds as well. Calcium, where is calcium? It's in what? Group 2A. So what does that mean? 2 dots. Argon. It's in, they don't show it here. 8A, 8 dots. So argon, 1, 2, 3, 4, 5, 6, 7, 8. I have an octet because my S and P sublevels are filled, because 2 go in the S, 6 goes in the P. When I have an S and P sublevel, that makes 6 plus 2 an octet. I'm happy. Boron, it's got 3 valence electrons. How do I know? How do I know? How do I know? How do I know? Where is it located? It's in the P block, second energy level in the first position. So it's 2p1. So someone might go, well, why is it 3a? Well, don't forget, to get to the P sublevel, I had to first fill the S, and it's a 2p2. So 2p2, 2p1, 3 valence electrons, boron, boom, boom, boom. I'm done. Well, that was a doozy. So I thank you for your patience. I'm sure you're going to have questions. I welcome them. You can post them on Ask a Question discussion board. You can email me. You have practice with your homework. But yeah, that was a challenging, lecture. This was one of the longer cuts, just because I covered a lot of material with the electron arrangement. I had to discuss energy levels. Within energy levels, there's sublevels. Within the sublevels, there's orbitals due to their orientation and shape around the nucleus. How to fill those using the full electron configuration, how to shortcut it with the condensed configuration where we use the closest noble gas to show the core electrons and then just write out the valence electrons, how to do the orbital diagrams to show the number of orbitals in each sublevel and follow Hund's rule, where we first fill or the electron goes in an empty orbital, and then we can show the spin up or spin down of the electrons, how to determine the number of unpaired electrons, and how to use core electrons to show Lewis dots. And for those unpaired electrons, we're seeing that later we're going to form bonds when we get to molecular geometry in a later chapter. So this was a doozy of a lecture. I appreciate you hanging in there. I thank you. And until next time, I'll talk to you soon. Bye.